Dear students, welcome to today's lecture, and we have reached section 5.2.5, and there we will show the solution of the Black-Scholes equation. In fact, we will work out the conditional expectation that we have seen last time. So where are we? What is the setting that we are in today? Well, we are dealing with a European call option where we know the payoff, V at time capital T is the maximum of ST minus K and 0, denoted by ST minus K plus. And the aim is to find the premium of the option at time T0, and particularly the value of the option at any time little t less than the maturity time capital T. Now this fair value, the fair value of the option, so the fair price of the option, that is obtained using the idea of hedging, a hedging portfolio or a self-financing portfolio. That's capital X T, little t from 0 to capital T, and it should satisfy that XT is equal to VT at any time little t between 0 and capital T. It is a portfolio consisting of stocks and cash. And when the stock should be delivered at final time, then there should also be stock in the portfolio. And if not, then there's only nothing left. Then there should be nothing left. So this is like the fair value of the option. At every time, the portfolio should replicate the value of the option. So also the discounted portfolio process should equal the discounted option value. Now, what we have seen in last lecture is that the discounted portfolio process, capital DT XT, T running from 0 to capital T, it is a martingale under the risk neutral measure P tilde. And therefore, we say the discounted portfolio process is equal to the discounted option value. So the option should be equal to V. We have also seen that V is a martingale. So the discounted V process is a martingale. And that means that, in fact, the expectation under the P tilde measure of the discounted process DT VT at capital T, given our knowledge until time little t, that should be equal to the discount process at little t times the option value at little t. Now, last time I've shown you the discount is e to the power minus the integral from 0 to t rs ds, and bringing this part to the right-hand side and combining it with this part gives us that the option value at time little t is the expectation under the P tilde measure of e to the power minus the integral from big T, from little t to big T, RU du, times the payoff, the value of the stock at final time minus K plus, given the filtration up to time little t. And now the next step is that we are going to look at the Black-Scholes-Merton model. So we make particular choices in this case for all the variables appearing. Particularly R, the interest rate process, is considered to be constant, little r. The volatility, sigma t, is also considered to be constant, sigma. And also the process alpha is considered to be just alpha. They are all constants in the Black-Scholes-Merton model. So if we then look at our portfolio process equal to our option value at time t, it is then the expectation under the P tilde measure of what we get in the end of, if we look at this and we just substitute little r here, it is just RT minus R little t. So that is, and the minus sign in front, right? The minus sign in front is also there. So we should keep that. So we get e to the power minus r capital T minus little t times the payoff, the maximum of S at final time minus k and 0, given the filtration up to time little t. The stock price process itself, with these constants that we have here, the stock price process itself is then equal S at little t is equal to S at 0, e to the power sigma times W tilde t minus W tilde 0, which is equal to 0, plus R minus 1/2 sigma squared times t. And with all these values constants, we end up with an easy expression. And particularly also for the stock value at final time, we can get its value, and that is S at capital T is equal to S0 e to the power sigma W tilde t plus R minus 1/2 sigma squared times t, where the t is the capital T. And we can also write this with st, with s little t, and that gives us then that S at final time capital T is equal to S at little t, e to the power sigma W tilde capital T minus W tilde little t plus R minus 1/2 sigma squared capital T minus little t. Now, in order to get the conditional expectation that we would be dealing with, this one, we will use the independence lemma. And the independence lemma was a lemma 2.3.4. But in order to do that, we first rewrite the value of the stock at the final time. Because if we look carefully back, we see that this is normally distributed with a mean 0 and variance t minus t. So we would like to get this into a standard normal distribution. So we do a scaling. And the scaling is as follows. We choose to name a variable capital Y, and that is W tilde t minus W tilde little t. We put a minus sign in front because then we get a minus sign in the exponent. That is typically nice. And we divide it by the square root of capital T minus little t. And then this variable Y, you see that this is standard normally distributed. And that is typically nice. And we can use it. So we replace W tilde capital T minus W tilde little t. We replace it by Y times the square root in the expression. So we end up with the stock value at capital T is the stock value at little t times e to the power minus sigma times the square root of capital T minus little t times capital Y plus, and the rest is just remains there. That is R minus 1/2 sigma square times capital T minus little t. Okay, and what we are looking for, again, let me remind you, the option value equal to the portfolio value, that is the expectation under the P tilde measure of e to the power minus R capital T minus little t times S T e to the power minus sigma square root of capital T minus little t times Y plus R minus 1/2 sigma square capital T minus little t. That is in the exponent minus k and then plus, right? Plus. So the maximum of this one and 0. Given our knowledge level, our filtration up to little t. And we know that ST is FT measurable, and Y, remember that is W tilde capital T minus W tilde little t, that is independent of FT. This is independent of FT. And therefore, we can use the independence lemma. We can make out of this a conditional expectation, depending on the filtration at t, we can make a regular expectation. And in order to do that, this is our measurable function. So we call this little c. So yeah, one part is FT measurable, the other part is independent of FT. And by the independence lemma, we first set st equal to x, a dummy variable, and then we can calculate this expression that we call c. It depends on t and it depends on this x. Yeah, it depends on this x. That is ft measurable, that we can see as an independent variable, in fact. So we can make out of this conditional expectation a regular expectation by means of this independence lemma. And the regular expectation is then the expectation under the p tilde measure of this expression, e to the power minus r capital T minus little t times x. Okay, so x times e to the power minus sigma square root of capital T minus t times y. And that remains, that is independent of ft, and that this makes it, therefore makes it a regular expectation. Plus the other part just remains, r minus 1/2 sigma square capital T minus little t. Then the exponent closes minus k plus. And now this is a regular expectation, so we can just write it out. Let's do that. That is an integral from minus infinity to infinity, just using the definition of the expectation, knowing that y is standard normally distributed, very important. That's a standard normal. So that we will be using, because an expectation is then, of course, the argument under the expectation sign times the density function of the standard normal dy. So let's do that. So that is the integral from minus infinity to infinity, e to the power minus r capital T minus little t times x, e to the power minus sigma, the square root of capital T minus t times little y. We are now, it's now an integration variable. So we are running over y here. So capital Y gets a little y, plus r minus 1/2 sigma square capital T minus t minus k, the maximum of this and 0, times the standard normal density function 1 divided by 1 over the square root of 2 pi e to the power minus 1/2 y squared dy. So we would like to get this expression. And a first important notion is the notion, when is this positive? When is this non-zero? It's the maximum of this expression and 0. So when is it 0 and when is it positive? And by this we can adapt the integration range, as you can imagine. When this is 0, we can just avoid it, remove it from the integration range. So the first question is, when is this positive? So let's check when the integrand is positive. When is this expression, x e to the power minus sigma, the square root of capital T minus little t times y plus r minus 1/2 sigma square times capital T minus little t, when is this larger than k? That is the first question, and that we can just work out. So we can get to a y version, y is equal to this and this. That is relatively easy. We take the log, etc., etc. So what we get if we do that, so this is calculus, maybe even high school. So what we get to, in order to get, we have something with e to the y. So we take the logarithm, etc., etc. We work this out. We divide first. We divide by x. Then we take the logarithm. So you see this already appear here. And then we get that y should be smaller than 1 divided by sigma times the square root of capital T minus little t times the log of x over k plus r minus 1/2 sigma square capital T minus little t. And this expression, so when this is satisfied, the argument is positive. Yeah. So this is like a bound for the integration range, and we call this d minus with arguments t minus t and x. You see x appearing, you see t minus t appearing here and here, and we just call this d minus of arguments t minus t and x. So we look for this expression over here, and we know when this is positive, when y is less than d minus, yeah, then this is positive. All right, so what we get is the following. Our option value at any time and for any x, c of t and x, that is then the integral from minus infinity to d minus of the parts that then remain, and the parts that remain, let's look at it again. We have this first part, an exponential, first part an exponential x times e to the power this, and times this. And that's the first part, and the second part is with the k. So the first part is the integral from minus infinity to d minus 1 over the square root of 2 pi times x times e to the power minus 1/2 y squared minus sigma, the square root of capital T minus little t times y minus 1/2 sigma square capital T minus small t dy. Yeah, that's the first part. And then minus k. So minus k. Again, let's look at it again. We have now copied essentially this part, this part, this part, this part, yeah, and also this part, right? And now we have that k part times this this density function. So we go on back. So we have this minus the integral from minus infinity to d minus with arguments capital T minus t and x of the term with k. 1 divided by the square root of 2 pi e to the power minus r capital T minus little t times k times this standard normal density function e to the power minus 1/2 y squared dy. Okay, let's see what we can do with this expression. Well, this part we can take out, and we recognize here immediately this is like the standard normal distribution. The standard normal distribution with the upper bound as the argument. Yeah. So let's first do that. First one we just copy here. 1 divided by the square root of 2 pi times x times this exponential function dy. And do we take something? Yeah, well, we can complete the square. You see, what we do, we see some term with y squared, some mixed term with y, and some term here. So together we can rewrite them by completing the square. E to the power minus 1/2, and then in brackets, y minus sigma square root of capital T minus little t square dy. And then that remaining part, we see the discount term, that's here. We see the k, that's here. And then the remaining part is, in fact, the standard normal distribution with as argument the upper bound here, d minus with argument t minus t x. Now, what can we do with that first part? Well, this makes life a little easier. We can do a variable transformation. Let's make this a z. And then dy is equal to dz. So let's look at this variable transformation. Y minus sigma, the square root of t minus t, we make it z. Dy, we make it dz. And as a result, we will also deal with a change in integration boundary. We move from y from minus infinity to d minus to z from minus infinity to d plus, in fact, where d plus is equal to d minus plus sigma times the square root of capital T minus t. So now looking at this equation after the variable transformation, we have taken the x and the square root of 1 over the square root of 2 pi. We have taken it out of the integration sign, and then what we recognize inside is just the standard normal with now the upper boundary for the integration range D plus with arguments capital T minus T and X. And that is, of course, the standard normal distribution with the 1 over the square root of 2 pi, the standard normal distribution with as argument D plus. So in total, we have found now the option value at any time T prior to maturity time for any X, X being ST. And that is X times the normal distribution with argument D plus minus e to the power minus R capital T minus little t times K times the normal distribution with argument D minus. So now substituting for X as T gives us, in fact, the value of the option at any time T. It's equal to the value of the portfolio process at any time T. And we write it as the call value with arguments T and ST. It's equal to ST times the normal distribution with argument D plus with the inner arguments T minus T and X minus e to the power minus RT minus T times K times the normal distribution with argument D minus with inner arguments T minus T and X. And this is in fact the famous Black-Scholes-Merton formula. It is the solution to the Black-Scholes equation, and it has been derived by Black and Scholes together and independently by Robert Merten. And it brought, as I mentioned, it brought the Nobel Prize to Myron Scholes and to Robert Merten, and Fisher Black passed away 2 years earlier. So this concludes today's talk. I thank you for your attention.